evening. Taylor series. So last time we looked at power series, right? What a power series is, radius of convergence, interval of convergence. We also discussed that every single function has a power series expansion. We did not discuss how to find that expansion. This is where Taylor series come in. Right, so Taylor series is the power series in which your a sub n is the nth derivative of f evaluated at your center x naught divided by n factorial. Bless you.
It's the nth derivative?
Mm-hmm.
Okay, so f, the little n means the derivative.
In parentheses means derivative. If the parentheses weren't there, it'd be a power.
Okay.
In the special case where your center is 0, it's called a Maclaurin series instead. I think this is Taylor's theorem. Basically says that the only power series expansion for a function is the Taylor series. There's more to the theorem. There's also an error associated with it, right? Because again, Taylor series expansion is just an approximation if you're doing polynomials. I'm not dealing with the error. I'm just gonna just put that in question mark because I don't know if that's actually Taylor's theorem. Taylor's theorem might be something else related to the series. But that is a theorem. that the only power series expansion is the Taylor series. Typically what we do is we just want we want a polynomial approximation for a function. Right, well, obviously an infinite degree polynomial is not really useful for that. So we also have Taylor polynomials. All of Taylor polynomials, so the nth degree Taylor polynomial is just the nth partial sum of the series, of the Taylor series. Some books cover them separately. I don't, because again, they're the same thing. Taylor polynomial is just a partial sum, so might as well cover them together. We already know some series. Some were derived in the video. 3 in particular. We have a series for e to the x. X to the n over n factorial. Valid for all x. Cosine of x. -1 to the n, x to the 2n over 2n factorial, also valid for all x. And we also have sine of x. -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial, also valid for all x. So these are known Maclaurin series expansions. Maclaurin series for cosine of x squared. Well, we could sit there, take derivatives till we start to recognize a pattern, and then try to come up with the series from there. Or we can use the fact that we already know the Maclaurin series for cosine. Start with cosine. Cosine of x squared.
What is being like all that, but squared? Okay.
Not the whole thing squared.
X squared?
Just replace x with x squared.
Okay.
And if x, or the absolute value of x squared less than infinity, what about absolute value of x?
Probably less than infinity.
Same thing, right? So that's just another way of writing for all x, all real numbers x. There's the Maclaurin series for cosine of x squared. Now keep in mind, whenever you're asked to find a series expansion, you must also include its interval. Right? It's not enough just to give me that sum. You also have to include the interval of definition. X e to the negative 2x. Again, we could sit there and take successive derivatives until we notice a pattern. Or we can use what we already know e to the x to be. So we start with e to the x. Now, e to the negative 2x. How do we do that?
Is it -2? to the n over n factorial. That's a negative 2x is what I, yeah.
And that's going to be for negative 2x, absolute value less than infinity. Write that as negative 1 to the n times 2 to the n over n factorial, all times x to the n. If absolute value negative 2x is less than infinity, what about absolute value of x?
So that's the infinity.
It'd still be all real numbers. So we have e to the negative 2x. Just multiply that series by x, right? Then we can just pull that x inside the summation. You wind up with x to the n plus 1. And that would be our Maclaurin series. First 5 terms of the Maclaurin series for e to the x times sine of x.
Does that mean we would have to find the Maclaurin series like we just did, then plug n in 5 times?
Don't have to worry about that,
Okay.
because we just want the first 5 terms.
Okay.
You don't actually have to try and determine the entire
Oh,
series expansion.
oh, you don't have to use it to find that?
I mean, we're going to use the process,
Okay.
but we don't actually have to worry about finding a pattern and finding the actual series.
Okay.
Right? Because what we're looking for essentially is a Taylor polynomial, right?
Mhm.
first thing we'll do is just define the function. E to the x times sine of x. Let's create the loop. I'm going to use a for loop. So with a for loop, need to define a starting value, n equals 0. The test. Right, so what values of n do we want the loop to run through?
To 4?
To 4, right?
Yeah.
So you want to do this as long as n is less than or equal to 4. I could also do n less than 5. That would also work. How does n change?
Yeah.
Right, we're just doing n plus plus here. Now it's the actual body of the for loop. So now what do I want to calculate? What do I want to do? I'm gonna have it print something. And so I want to clarify what derivative I'm looking at. So I'll say like the n derivative at x naught is, and now I want to actually print out the derivative. Capital D, command for derivative. What are we taking the derivative of? F of x. If I just do x like this and then close it out, it'll only calculate the first derivative. I want it to calculate the nth derivative. So what we do is we put it in braces. With respect to what? Comma, the degree of the derivative. However, that's going to give a function. I want it to be evaluated. I think it's this order. Backslash period, x, arrow 0. This whole thing here means whatever's in front of it, we're going to evaluate it at, in this case, x equals 0, when x is 0. That's all I want. What I might do here is put in this. There you go. Now, I could even go even further. Why not just have it evaluate the bloody term? The coefficient instead of just the derivative. So I'm going to keep that print command in there. I'll do another one as well. Right, just so we can see what the derivative is and then what is the coefficient. It's going to be almost the same. I'll just take that out now. I don't need that comment anymore. Call it the n coefficient. I still want that derivative, but now we want to divide it by n factorial, don't we? Because remember, it's the nth derivative at x naught divided by n factorial. And now we'll get a list of the derivatives and coefficients. And so I would probably not include this line here. Right, simply because it's unneeded. I'm just doing it for demonstration purposes. Oops. You're not even going to give me the option to paste it as a picture, are you? Oh, you suck. All right, so I'm going to have to, just so I can screenshot it. That is so aggravating, actually. Screenshot that. I'll put that there. Now let's go ahead and remove that. We're looking for the fourth degree Taylor polynomial. First coefficient is 0, right? So 0x to the 0 plus 1x to the first, 2x squared, 2x cubed, and 0x to the fourth. No, that's not right. Now I remember what I have to do. Let's put the n factorial in parentheses. Right, and then, no, I also have to put this in parentheses, I think. Yes. I wonder if I would have just play around. If I do this, remove the parentheses, and then here, put that out there instead. Would that work? No, it wouldn't. Okay. No, so I had to do it that way. You. Okay, there we go. That's better. So 0, 1, 1, a third, and then 0. Now, why aren't you going away? There we go. See that? Clorine series for inverse sine. Now, to show you what's going to happen if don't need these comments anymore. Actually, that entire line I can just get rid of now. I don't want it. So we're going to want several terms, right, to see if we can find a pattern. Let's do 11 terms. 9 terms. 10 terms, rather. We'll go up to n less than equal to 9, see what we get. Other than only having the odd terms, do you see a discernible pattern? The fact that it's taken this long means the answer is no. There is a pattern. You just can't determine it from this information. Mathematics is wonderful, but it's also stupid. Our best bet here is going to be to do it by hand. Because when we do it by hand, we can write it however we want to make the pattern easier to see. But there is a problem. Derivative of inverse sine. That's not too difficult. What is its derivative?
It's 1 over radical 1 minus x squared.
What is that derivative?
Oh, the derivative of 1.
So now we're looking for the second derivative. I don't actually care. The point is, it's going to be a function of x divided by a function of x. Because of chain rule.
Yeah.
Which means every single derivative after the second is going to require the use of quotient rule. Damn that. Well, inverse sine of x plus c is going to be the antiderivative dx over the square root of 1 minus x squared. C is a constant, so it actually doesn't matter what side we write it on. So the inverse sign is going to be c plus that antiderivative, that simple antiderivative. Okay, so if we now look at the function 1 over the square root of 1 minus x squared, we're going to run into the exact same problem. First derivative is going to give you a function of x divided by a function of x, which means we're still going to need quotient rule. But what if we'll start with that. These derivatives are no longer going to require quotient rule. Then once we get the expansion for that, we just replace x with x squared. That will give us this. And then we can take that antiderivative to get the inverse sign. That's the path we're going to go down. So we'll find the Maclaurin expansion for 1 over the square root of 1 minus x. I don't need to be that long, but I'm going to create a table. And just to represent the derivative we're looking at, column for what that derivative actually is. And then a column for evaluating it at 0. Start with the 0. It's just the original function, right? When x is 0, what do you get?
1.
Maybe I will keep the ruler. And then I'll actually do these lines, which I typically don't do, but First derivative. So now what is the derivative of that previous line, that previous entry? So what is the derivative of 1 over the square root of 1 minus x?
Just one.
So let's return to basics, Calc 1. First, look at this as a power function.
Right.
What's the power?
-1.
I agree it's negative, but the power is not 1. It's negative a half. What's the derivative of a power function? All right, so what's the derivative of u to the minus 1/2?
Yeah, u to the negative, it'll be something to u to -3/2. -1/2 u to -3/2.
Now we need to multiply that by the derivative of u. What's the derivative of 1 minus x?
1. -1?
-1.
-1, yeah.
Put it all together.
-1 times. So 1/2 x to the -3/2.
Or 1 over 2 times 1 minus x to the 3/2. I don't know how I want to write it. I will do it that way. Evaluate that at 0.
As an x at 0, right?
Mhm.
It's 1/2, right?
Oh, go away, Mr. Scheduled Scan. Second derivative. So what is the derivative of that previous entry?
So -3/4 x to the -5 power.
Close. Very close. What's the derivative of 1 minus x?
Oh, okay. So I should have said u then substitute in. So the root of 1 minus x is -1. So
No.
that means, okay.
Oh, yeah. Minus 1 is the derivative,
So
right?
that would make this just 3/4.
Yes, right. However, I'm not going to write it as 3/4. I'll write it as 3 times 1 over 2 squared. The reason for that will become apparent very shortly. Now evaluate that when x is 0. Let's look at the third derivative. So now what is the derivative of that previous entry?
U. That's just one. So is it 15 8 to the negative 7 halves?
And again, I am not going to write it that way. Let's check out one more just to be certain. What is the fourth derivative?
So 1/5 by 3 by 1 over 2 to the power of 4 multiplied by 1 minus x to the power of minus 9 over 2.
If I were to ask you for the general term, could you tell me what it is? So again, that is no, ignore the over n factorial. Just generally speaking, what would the nth derivative be at 0? That's what I'm asking for the general term.
So we're trying to write write that in a formula for that show the pattern.
Mm-hmm.
Okay. Yeah, because I see the pattern. I'm just trying to think of how to express it.
Well, start with what we know. We're gonna have a fraction.
And it's going to be 2.
It's definitely gonna be 2 to a power in the denominator. What's the power? Now, what about the numerator?
It's going to be n minus 1 or n plus 1.
Is going to be an minus 1 multiplied by.
The thing is, I'm noticing in the fourth one that the power of 2 is even, but all the other ones are odd.
Are they?
On the top.
Are they?
All the numbers that are being multiplied, I mean.
Okay, can't be bothered. The powers of 2 are not all odd, right?
Oh, there's a factorial at the top, isn't there?
Actually, that's not fair. I do know. I'm just not going to spoil it just yet.
Is there like a 2n factorial or something?
It's not 2n factorial.
N plus 2 factorial?
So when n equals 1, numerator is just 1, right?
Right.
N equals 2, you get 3 times 1. N equals 3, you get 5 times 3 times 1. N equals 4, you get 7 times 3 times 5 times 3 times 1.
Is it a double factorial?
So it's going to be a double factorial. Can't be a factorial because we're skipping every other term.
Okay.
So it's definitely going to be a double factorial. What do you notice about all of the terms in the numerator? They're odds.
So it's going to be an n plus 1 double factorial or n minus 1?
That's not going to give you odds. That'll give you odds and then evens and then odds and then evens and then odds and then evens.
Is it an n plus 2 factorial? N minus.
That's the same thing. You'll get odds and evens, odds and evens, odds and evens.
Or did I forget to say double factorial?
Definition of odd is what?
Even.
That's not very helpful.
Not divisible by 2?
More specifically.
Like no thing like that.
It's a remainder of 1. 2n plus 1. But 2n plus 1 won't work here, will it? Because if at 1, it would be 3. At 2, it would be 5. At 3, it would be 7. At 4, it would be 9.
Would it be 2n minus 1?
Two n minus 1 double factorial all over 2 to the n. But if n equals 0, you get negative 1 double factorial, which is undefined. This is only valid for n greater than or equal to 1. Take that whole thing, divide by n factorial. I don't think I need my ruler anymore. Two n minus 1 double factorial all over 2 to the n times n factorial. That can be simplified. The numerator can't be, but the denominator can be. So we want to look at n factorial. We know what that is. Right? Two to the n. And 2 times itself n times. Notice n factorial also has n terms. Multiplication is commutative and associative, isn't it?
Yes.
Multiply each of those terms by 2. There's still n terms, right? What do you notice about each of those terms, though?
They're all 2 in front of them.
Which is the definition of what?
Even.
Even.
Mhm.
Notice it skips the odd terms. Isn't that the definition of 2n double factorial?
Yes, it is. So,
This is our general term, or our general coefficient, rather.
oh, that doesn't get simplified anymore?
Nope.
Okay.
Can't be. But again, that was only for n equals 1 to infinity, not 0. So we have to just add in the 0 term. So it's 1 plus a series from n equals 1 to infinity. And then all times x to the n. We need an interval definition. No. Look at that limit. that just becomes what? The limit of 2n plus 1 all over 2n plus 2? Oh, yeah, I forgot the x's in there. So let's do x to the n plus 1 there. X to the n down there. And that'll be absolute value of x times that limit. What's that limit?
One.
So we get absolute value of x less than 1. I'm going to leave it as an exercise that the series diverges at the two endpoints. You have to show that. So interval of definition, open interval -1 to +1. Good. Now we can find one over the square root of 1 minus x squared. Right. Same thing, except it's now x to the 2n. Right? Now, we can find the inverse sine of x. It's going to be c plus the simple antiderivative of the expansion. What is the antiderivative of 1?
1. So, c. 1 plus c.
It's just x.
Oh, yeah.
Now remember, when you do antiderivatives of sums, it's the sum of the antiderivative, and you don't lose a term, right? So it's still n equals 1 to infinity. That's going to be a constant. Now, what is the antiderivative of x to the 2n?
Is 2n times x to the power of 2n minus 1.
You gave me the derivative, not antiderivative.
Oh, okay. So it's actually x over 2n to the 2n plus 1 power. If not,
What's the new power of x?
actually, oh, it's not x over 2, it's 2n plus 1 x times x, right? That's not
So what's the new power of x?
2n plus 1 over 2n plus 1. Okay.
We need to find a value for that c. We can't just leave it as c. Well, notice what's going to happen. Evaluate this at the center. This is just going to be a bunch of zeros, isn't it? That sum. And that x is going to be 0. So inverse sine of 0 has to be c. But what is the inverse sine of 0?
Zero.
0. There's our expansion for inverse sine of x.
Oh, one problem.
That was one problem. It was a fun one, too.
Yeah.
Good. And again, I also cut out the endpoints, proving that the endpoints diverge. So this problem is actually longer. Purpose of this problem: do not become absolutely dependent on a calculator. You never would have gotten that pattern from that. Right? Because that pattern, that term is 2n minus 1 double factorial over 2n plus 1 times 2n double factorial. You would have had no way of getting that. You might have gotten lucky and stumbled. Well, even the numerator you're not going to be able to do because it's simplifying. right? That 5 would have thrown you off. That's not 2n minus 1 double factorial. So do not become dependent on your calculator. It's actually pretty stupid. No. Find the first the first 4 non-zero terms of the Maclaurin series for secant of x. Notice a key difference between what this one's asking and what this one was asking. They wanted the first 5 terms there. Here they want the first 4 non-zero terms. That is not the first 5 non-zero terms, is it?
No, it's only the first 4.
4?
3.
Yeah, there's only 3 non-zero terms there. So we would have had to keep going if that was asking for the non-zero terms. So this is not how I did it, so I'm gonna do this blind. I think I know how I want to do it. So I'm going to define, of course, f of x, secant of x. Yep, that's all I want. No, it's not. Define a variable non-zero. I'm going to start it at 0, right? Because we have no non-zero terms right now. Let's do a while loop. While non-zero, we want what for? So while we have less than 4 non-zero terms, this is what I want it to do. Calculate, what do I want to call it? Oh, I need to also start and it's 0. Let's call it A of n to represent the coefficient. So I want to calculate that, right? That's going to be our coefficient. going to use an if. And this is where I don't remember. Documentation. If. Can I do multiple? Don't know if I can actually do it or not. Let's try. No, it's not going to let me, is it? Before I do that, let's do a print command. Print. The n efficient is print out a sub n. Now I want to do the if a sub n equals 0, non-zero equals non-zero. I don't want to add anything, right? Else, actually, I think I can just do this. Else, add 1 to non-zero, right? So, if the coefficient turns out to be 0, don't change the non-zero. If it is not 0, then I'm going to add 1 to the non-zero. And as the very last thing I wanted to do, I then want to add 1 to n. And it's very important that that n++ comes last. Because it does this in order. This should work. Oh dear. Apparently not. Shin. Bort. Oh, I know why. I had to put a double equals there. Yep. So there we go. So we have T6 is what we want. It's 1 plus x squared over 2 okay, that's right. Plus 5x to the 4th over 24 plus 61x to the 6th over 720. If that's what we were looking for. Now you could do this by hand if you really wanted to. I'm warning you that derivatives get really messy really quickly. Good. Questions on Taylor series? So you can work on the 22nd assignment. Remember that is going, all of those assignments will be due on May 8th. That is the day of the final. Also, don't forget the replies to the third discussion assignment are due tonight. We only have 2 weeks left. Next week, and by next week I mean Wednesday and Monday, we work on parametric equations. Right, so Wednesday will be what are parametric equations. We'll look at plotting some. Right, we'll define them. Look at some common parameterizations. Wednesday will then be the calculus of parametric equations. So this is essentially analytic geometry, geometry of the plane. So we're going to be looking at a more in-depth study of two-dimensional geometry. This is pre-Calc 3. In Calc 3, you'll extend this idea to 3 dimensions. The week after that is polar. So again, the Wednesday we'll do polar coordinates. What are they? How do we convert? Polar curves. What are polar curves? How can we represent them? We'll plot some. And then that following Monday would be the calculus of polar curves. And then that would be it. The Wednesday after that is the final. So that's how the rest of the semester is going to go. See you again on Wednesday.
Yeah.
Mm-hmm. You too.